All good? Everybody can hear me? Okay, so welcome back. Another great session ahead. Some foundational work and some more practical results. We are going to start with Anubhav, talking about foundational work on trade-offs between time-space for Sumcheck. So please, go ahead.
Awesome. Thank you so much. Am I ready to go? Oh, hi. Welcome back, everyone. So now I'll be talking about like some time-space trade-offs for Sumcheck. And so this talk is going to involve like an upper bound proof and a lower bound proof. So hopefully there's going to be something for like everyone in this talk. This paper appeared at ECC 2025, and it's joint work with the wonderful folks at EPFL, ETH Zurich, and Penn. Oh, the clicker, I don't think is, I think it's not configured to the slide. Okay, thank you. Okay, again, SNARKs are succinct non-interactive arguments of knowledge, which help a prover convince a verifier for a statement with a short proof. And recent work on SNARKs uses Sumcheck as a building block, as all of you might already be familiar with. And this appears in all sorts of like different ways, whether that be through streaming SNARKs, ZKVMs, memory checking arguments, all sorts of different PIOPs, you name it. So therefore, the space-time efficiency of SNARKs crucially relies on the space-time efficiency of Sumcheck provers. And what is Sumcheck? Just to recap very briefly, given a multivariate polynomial f and a target sum sigma, a prover convinces a verifier that the sum over the Boolean hypercube of the evaluations of that particular function f equals sigma. Existing Sumcheck provers already exist, and they're already very, very efficient. So let's talk about like two of them. They are the folding-based Sumcheck of CTY11 and the log-based Sumcheck of CMT12. The folding-based Sumcheck is very, very fast. It is like optimal linear time, but it suffers from the fact that it requires like linear space, and it's like you use a lot of space. On the other hand, the log-based Sumcheck has this additional log n factor in time, and therefore it's like concretely also like quite inefficient. But it is space optimal. The only thing it really stores is the random challenges that the verifier sends, and really nothing else. So naturally, the question is, can we get prover algorithms which have time and space that is somewhere in the middle? Okay. And additionally, can we also prove lower bounds for space-time trade-offs? And an additional question can be that, can we get better trade-offs by departing from the interactive proof model, by just changing how the Sumcheck protocol is implemented? Okay. For the remainder of this talk, our model of time is going to be number of field operation, and our model of space is going to be the number of field elements that are stored by the prover. Great. So just to summarize our results, we propose Sumcheck. We both propose upper bounds and lower bounds for both Sumcheck over multilinear polynomials and product of multilinear polynomials. Product of multilinear polynomials is a case that covers practically all like relevant applications for SNARKs. And in this talk and in the paper, we mostly focus on product of two multilinear polynomials, but the results extend reasonably well to more polynomials as well. So for multilinear polynomials, we get that if you have space that's n to the 1 over k, then you require time that's only kn, where k can be any parameter that you want to choose. And for our lower bound, we get the fact that if your space is at most n to the 1 over k, then you must use a time that's at least kn. So our Sumcheck algorithm for multilinear polynomials is in fact tight. Great. On the other hand, for product of multilinear polynomials, we get this additional log n additive factor in the time if you have the same space n to the 1 over k. And that might seem like kind of strange, like why do you have a log n factor out of all the possible things you could have? But we show that this log factor is in some ways inherent. That if your space is at most n to the half minus epsilon, then you actually do require n log n time. So one example of the upper bound is that if you set k equals 2, then you get squared space and n log log n time. And just one additional thing, that this lower bound is conditional on some natural conjectures that we make about the multiplication of multilinear polynomials. Because if it were not conditional, and in fact, for example, if you had matrix multiplication that you could do in n squared time, then this lower bound would not hold. And in fact, you could get an upper bound for product of multilinear polynomials that matches the one for product of multilinear polynomials that matches the one for multilinear polynomials. Great. And additionally, we also answer the third question raised on the previous slide, which is that in the PIOP model, where the prover can now send polynomial oracles in addition to just like plain text messages, you can then achieve n to the 1 over k space and k plus log star n time. So as opposed to log log n, you get log star. But we won't discuss this in today's talk. So we kind of want to, I guess, summarize our results in this, I guess, graph for our product of multilinear polynomials. So first of all, the CTY11 result can be seen as linear space, linear time, and the CMT12 is n log n time, log n space. And then additionally, from our result, we get like two maybe interesting parameterizations, which are that you can get square root n space and n log log n time, or you could get log n space and n log n over log log n time. So that strictly improves upon the CMT12 algorithm. And our upper bound, of course, can be interpolated through all possible values of k that you might want to set. And then our lower bound is also starts, I guess, becoming more and more relevant when your space is smaller than square root n. And we also show that you can then bypass this lower bound in the PIOP model if you're willing to send polynomial oracles. Okay, fantastic. Okay, just to recap. So these are the final results that we get for the asymptotic results that we get for Sumcheck over product of polynomials. Now you might say that, okay, I have this like O of n log log n plus k. If I really want to implement this Sumcheck, if I want to implement the Sumcheck prover, I don't just care about like big old time complexity, right? I actually want to figure out, you want to be assured that I'm not hiding like 1,000 factor in like the big O notation over there, right? So therefore, we also implemented this protocol, and I think we get like some reasonable numbers. So we implemented over like a 128-bit field, and we set n to be 28. And in that case, what happens? First of all, the folding-based Sumcheck, as you can expect, is very fast, but it takes like 7 gigs of memory. The log-space Sumcheck is very slow, but it takes basically no memory. And for a new result, you can parameterize it in a number of ways. So one way is if you set k equals 2, then you can get a time that is reasonably close to the folding-based Sumcheck. So you have an overhead of about like 1.85. But your memory requirement goes down by like a factor of 120. And then if you are happy to pay in with a little bit more time, then you can, of course, change the parameterization and set k to be equal to 4 and get memory that's like very, very close to the log space Sumcheck and still be way faster than what the log space Sumcheck gives you. OK. So now we'll just discuss some background before we move on to our constructions and our lower bounds. First of all, OK, what are multilinear polynomials? They are polynomials where the degree in each variable is at most 1. They have a very nice Lagrange basis representation, which means that they can be represented uniquely with their evaluations over the Boolean hypercube. And in particular, they are the random linear combination of their evaluations over the Boolean hypercube, where the coefficients are these Lagrange basis coefficients. And these Lagrange basis coefficients are, of course, very efficient to compute. And the model for our upper bounds that we want to consider in this work is the streaming access model, where the input to the prover is a stream to the evaluations over the Boolean hypercube of this polynomial. So at first, like you have a pointer that's like pointing to the 0th evaluation over the Boolean hypercube. Then you press next, and you get the next evaluation. You press next, you get the next evaluation, and so on. That's our model. OK, and we'll briefly recap what Sumcheck is. We want to prove that the sum over the Boolean hypercube is equal to sigma, and the verifier has oracle access to the polynomial. In the first round, the prover sends this h1x1 polynomial, which is the first round polynomial. And it is important to, I guess, like remember what the structure of this round polynomial looks like. So what's happening here is that you're summing over all the last n minus 1 variables, and you're only setting the first, you're only keeping the first variable as a variable. Okay. Then the verifier performs the check and sends back a random challenge. And the next round, now the prover, for the second round, prover defines a new round polynomial where the first variable is now set to the random challenge that the verifier sent. The second variable is still now a variable, and you sum over all the remaining n minus 2 variables. And then this pattern continues. And so this is what broadly the Sumcheck protocol looks like, and these are the checks that the verifier performs. For the purposes of this talk, we're not going to change the Sumcheck protocol itself. The Sumcheck protocol is going to remain the exact same. What we are really concerned with, how the Sumcheck prover is implemented. So the questions that we actually want to ask are how the prover actually computes these round polynomials and how it maintains its internal storage across these different rounds. Okay, so we'll go over the prover algorithm for multilinear Sumcheck, which, as you might recall, requires only linear time if you set k equals 2. And the thing that we'll do here is that we'll try to do something that's kind of in the middle of the folding-based Sumcheck and the log-space Sumcheck. In the folding-based Sumcheck, the only time you actually read the input stream is in round 1, and that's it. And because you are okay with getting linear space in that algorithm, you just store these things called folded polynomials, and therefore you just never have to read the input streams ever again. You just read them in round 1 and never again. On the other hand, log space algorithm, it's the other end of the extreme. You read the input streams in all n rounds, and you store nothing at all except the random challenges. So we want to do something in the middle. So the most middling thing I guess you can do is read input streams in 2 rounds, which are rounds 1 and the middle round, n over 2. Now we will use square root n space, and what we will store are these things called sums of subcubes, which I'll get to in the next slide. Okay, so what do you do in the first n over 2 rounds? The high-level idea is you want to be able to store all the necessary information in round 1 that allows you to compute the round polynomials of the first n over 2 rounds. Okay, so to that effect, we introduce a notion of a generalized round polynomial. So in the regular round polynomial, what were we doing? We were just keeping one variable a variable, and we were summing over everything else. Now, we're going to keep the first n over 2 variables, and we're going to sum over the remaining n over 2 variables. Okay, and the reason this is nice, this is a nice abstraction, is because say you are able to compute and store this polynomial somehow, then you can plug in any value of R1 through Rn over 2 that you see later to be able to compute the appropriate round polynomial. And therefore, you would not need to read the input streams in rounds 2 through n over 2. And the next time you will read the input stream will be in round n over 2 plus 1, and you'll be happy. Okay, but the question is now, okay, how do you actually compute and store this generalized round polynomial? And we will use our best friend for this talk, Lagrange interpolation, which is that you expand this function out into its Lagrange representation, and then you just change the ordering of the sums, and you get this particular expression. And this expression is particularly nice because it has this like kind of structure where only the outer sum depends on these variables. You have this outer sum and this inner sum. The inner sum does not depend on x1 through xn over 2 at all. It's just like a function of the polynomial. It is not a function of the random challenges that you have not seen yet at all. So because it's not a function of those things at all, you can immediately just right now store them. Okay. And if you do store them, which means that you're storing these expressions for all x in 0, 1 to the n over 2, that means that eventually once you get R1 through Rn over 2, you can plug it back into this expression and compute the appropriate round polynomial. And so how much storage have I actually used here? I've only used square root n space, which is equal to the n over 2. Okay. So that's what you do for the first n over 2 rounds. What do you do for the last n over 2 rounds? You do something very similar. In round n over 2 plus 1, you compute this new generalized round polynomial where the last n over 2 variables are variables and the first n over 2 variables, you know what the random challenges are now. So you can just set them to be R1 through Rn over 2. Okay, and again, you would expand this through Lagrange interpolation. You will get that expression. And you can then see that one value of this expression can be computed in only square root n time. And there are square root n many values that you need to represent this polynomial. And therefore, computing it in total would take linear time. And of course, storing it, of course, only again takes 2 to the n over 2 time, which is equal to square root n space, which is the same as before. So in both rounds, we have computed like some store. We have only used square root n space so that you can then later on compute the round polynomials for the next n over 2 rounds. And that is the entire algorithm for the multilinear sum check. Now, you might be asking, okay, where does the log n show up in the sum check for products? So in today's talk, I'm not actually going to go over the product sum check protocol because I want to also go over the lower bound. But I want to give you some motivation for like how this log n shows up and why it's kind of necessary. So in multilinear sum check, what we saw was that we could get away with 2 passes in rounds 1 and n over 2, and that's it. And each pass required linear time. So let's see what happens if you just like try to do a product sum check for k equals 2, and we make passes in only rounds 1 and n over 2. So in that case, if you try to do that, then you would have to compute this generalized round polynomial, which now looks like, instead of just a sum over m1s, now it's a sum over products of m1s and m2s. And these m1s and m2s are themselves multivariate n over 2 variate polynomials. And in general, multiplying polynomials is a hard problem. Like, we do not know a linear time algorithm for it, right? And that is sort of why, if you were to try to do this and like store this round polynomial in one go, you would need way more than linear time. And you, of course, will not get overall linear time because you're just spending more than linear time in just one single round. Okay, but what you can do is you can change your algorithm to make passes in only rounds 1, 2, 4, 8, essentially powers of 2. And then it kind of turns out that even if you do this polynomial multiplication naively, without like using any fancy FFTs or anything like that, even if you do it naively, then you would only require linear time in each such round. And how many rounds are there? There are log of little n equals log of big N many rounds. Okay, so that's pretty nice. But in reality, when you actually implement the protocol, it doesn't, choosing like powers of 2 is not necessarily like the most optimal thing to do in terms of like concrete time. So in these numbers that I showed you at the beginning of the talk, these numbers are not obtained from making passes of the input streams in round 1, 2, 4, 8, and so on. In this case, we made passes in rounds that were like 1, 2, 3, 5, 8, 13, which, I mean, might look familiar. I mean, it's like the Fibonacci sequence, one of the most famous sequence of numbers. Is that a coincidence? Yeah, it is actually a coincidence. There's nothing fundamental here going on. And because we could have honestly just chosen like a slightly different set of rounds if we wanted like a slightly slower prover and we want our memory budget was slightly lower. Okay, but the key takeaway from, I guess, this slide is that our algorithm can be parameterized based on our specific memory budget. So the way you would choose what rounds to actually make passes in is that you would specify some memory budget. You would have like some 20 megabyte memory budget, and then you can figure out what the optimal set of rounds to make these passes are from your memory budget to optimize your prover time. Okay, so that's all I have to say about the upper bound. And now I want to talk a little bit about the lower bound for multilinear sum check. Okay, so as lower bounds usually go, I think sometimes you need just like a little bit of time to even explain what your result is. And that is what this slide is going to do. It's just going to explain what the result is. So the model that we used for our upper bound was streaming access to multilinear polynomials. For our lower bound, we actually want to do something stronger. We want to prove lower bounds in a random access model. Mainly because if we only proved lower bounds in like this particular streaming model where we are assuming that, oh, our evaluations are arriving to us in like a particular order, then it's possible that we are not ruling out the existence of algorithms that maybe get their evaluations in a completely different order, and maybe that's like a fine for us. So we want a very general lower bound so that we can show that there's no trickery you can do behind like changing the ordering of your input or anything like that to get a better algorithm. Okay. Another plus point of our algorithm, of our lower bound, is that the lower bound is not just on the number of field operations that the prover algorithm has to make, but it's on the number of input accesses. So now because we have specified that we are in the random access model, we can talk about, oh, this is like the number of input accesses that the prover makes throughout its execution. And of course, the total time is going to be like strictly more than the number of input accesses that the prover makes. The only, I think, negative point about this lower bound is that you have to kind of assume that the prover is non-adaptive with respect to the polynomial and random challenges. So non-adaptive here just means that whatever accesses that the prover is making to its input don't change with what random challenges it sees. And this is maybe not the worst thing in the world, because we already kind of do know that like all existing Sumcheck provers like ours and the ones that came before us are non-adaptive. And at least to me, like right now, it does not seem that there's anything you can really do with an adaptive Sumcheck prover, but maybe I'm wrong, and I would love to be wrong. Okay. So the lower bound that was stated in the results section was that if you have space that is n to the 1 over k, then you require time that is at least kn. This expression is kind of unwieldy, but it can be transformed into this very simple and clean expression, which is that t log s is at least omega n log n. These two things are equivalent. And then furthermore, you can kind of rearrange things to just say that t is at least n times log n over log s. Okay. So if you want to prove like that t is at least n times log n over log s, then one thing that you can try to show is that you need to read at least omega n input elements every log n over log s many rounds. And if you prove that, then of course you will end up with the lower bound. Fantastic. Now we have to introduce the notion of the prover, the Sumcheck prover, as in some ways a multi-party prover. What do I mean by that? So right now we have been thinking of the prover as this like monolithic thing, which is which exists like all throughout n rounds of the Sumcheck protocol. It has some internal storage. It receives the input, which is m, and it computes the round polynomial in each round, and it updates the storage in each round. But we should not necessarily think of the prover for the purposes of the lower bound in this way. We should think of it as n different provers, where n is the number of rounds, where you have one prover for round 1 and one prover for round s plus 1, where this little s is defined as log of big S. Big S was our space bound. And then so on and so forth. So you have 2s plus 1, around 2s plus 1 prover, and so on and so forth. So in total, you have log n over log s many parties that you're interested in. And because the prover is ultimately like just one party, what we can actually try to say is that the communication between the round 1 prover and the round s plus 1 prover must be at most s if the overall space bound on the prover is s, right? Okay. And that also goes for the other pairs of rounds as well. And what we can now, I guess, simplify our goal to is that we can say that if we just look at this communication problem between the round 1 prover and the round s plus 1 prover, then we want to show that if the communication from party 1 to party 2 was at most s, then party 2 must make n reads to the input in order to maintain completeness. Okay. And we'll rename these two parties, as in like all communication protocols, to Alice and Bob. OK, so now you have a round one prover, which sends over some storage over to the round s+1 prover, whose inputs are the input polynomial m, the target sum sigma, the random challenges it has seen so far, so R1 through RS, and this storage that the round one prover is sending to it. And its goal is to now compute the round polynomial, which is defined as follows. Because we know that this prover must be complete, and therefore it must return the correct round polynomial for all of these different possible values of R. So here, we are just considering, even though the random challenges can be any elements from the field, we only really need to consider all the binary challenges, all possible binary challenges. So in particular, if the challenges were 0, 0, 0, 0, then the round s+1 prover must be able to like return the correct round polynomial corresponding to those values of R. And that is true for all of these possible values of R. And because of that, it must be true that the round s+1 prover can compute all of these different possible sums. And these sums just like are the values that you get when you plug in these values of R into that expression over there. OK? And how many sums are there? There are 2 to the little s+1 equals 2s many sums. And it is able to compute these 2s many sums from pi and m. However, we also know that pi, the size of pi, sorry, that's a typo. The size of pi is at most 2, as at most s. And therefore, there must be at least s many sums that are computed by directly reading from m. Right? Because there are sums, because of just the storage constraints, there are some sums for which the storage cannot help the prover at all, and it must resort to reading directly from the input. OK, and this is point 3 that we will use in the next slide, which is that s many sums are computed by directly reading from m. And now each sum is of the form, it's like a sum of like the evaluations over the Boolean hypercube of these many elements. And all of these sums are disjoint subcubes. So you can think of them as like s many subcubes, each of size 2 to the n minus little s minus 1, which is 2 to the which is n over 2s many input field elements. And if the prover is able to actually correctly return all of the sums of these subcubes, and all of these elements in these subcubes are themselves like arbitrary field elements, then it would have to read all of these values in order to be able to correctly return the sums of these subcubes. It can't avoid it cannot get away with not reading even a single one of them. And therefore, the prover would need to read at least n over 2s times s equals n over 2 many input elements total. And that is, we have now achieved our new goal that we set before. And we can now similarly show a similar statement like we did for round s+1 for the remaining rounds, 2s+1, 3s+1, and so on and so forth, that you need to read at least omega n many input elements in all of these rounds. And that gives you the final lower bound. And that is all I have for the proof of the lower bound. And again, in summary, we get like these 3 new results: upper bounds, lower bounds, better results in the PIOP model. And this is all the stuff that we proved in our paper, which you can find on this link, and you can find the implementation on this link. So thank you. Yep.
Amazing. Thank you very much. One quick question. For one question, we have time.
Yes, I was just curious to know if you tried to prove some upper bounds on other models like the one we saw this morning where there are multiple heads, that can jump around, or even in the random access model.
We were only considered with the single head streaming access model. For the multiple head model, I think that is like an interesting problem. And
Yeah, because there's a mismatch in model, right? In the lower bounds, you
but-
chose the sort of the best model to prove the lower bound. And
But no, but like the thing is that the lower bounds are in a stronger model. So it's not that, so you can't actually, even if you like relax the model like a little bit, even if you made the model like random access, in that regime, at least if you made a random access, then you would not be able to get a better algorithm. But the multiple heads thing, I think maybe you can get away, if you have like a non-constant number of heads, maybe you can come up with like an interesting parameterization.
Yeah, for the upper bound. Yeah, that's what
Yeah.
I was thinking. Okay.
Amazing, thank you. Let's thank the speaker again.